when we met last, we talked about, or rather, we derived the different moduli, the Young's modulus for length, elasticity. We talked about the shear modulus, and we talked about the bulk modulus, and how you can relate the bulk modulus to compressibility. So that's something that we talked about. So now, today, like I said, we'll basically be going through the questions. Okay, so we'll be going through the questions, and then I will see just how much we'll be able to cover. So this question says a vertical steel. A vertical steel beam supports a load of 60,000 newtons. If the length of the beam is 4 meters and its cross-sectional area is 8 times 10 to the power negative 3 meter square, find the distance the beam is compressed along its length. What maximum load in newtons could the steel beam support before failing? Okay, so from that particular question, some things have to come to mind. So what you have to talk about first of all is with regards to what are you dealing with first of all, the material. So there you're dealing with steel. So that's important because when you go to your table, when you're looking for these strengths and everything, the Young's modulus, the material is important. You miss the material, you get a wrong Young's modulus. You get a wrong Young's modulus, everything goes wrong, isn't it? So that's important. Then the other thing that you want to ask yourself is what kind of of stress is this material undergoing, or rather, is it being put or on in rather or under? So you see here it's what compression. So why is this important? Because as you will see, and like I showed us last time to say, there are these values which you call what the ultimate strength of materials, right? So the ultimate strength of materials, they differ depending on whether it's what. So you see, it differs depending whether it's tensile strength or compressive strength, right? So that's why it's very important to be able to pick out all these things out of the question, so that even as you are starting to solve the question, you are well aware to say, okay, this is what I'm looking at, and so that then becomes very important. So I think from me, those are really the points of concern. I think having done that, I think the rest is just us really just solving. So of course the formula, so here we are talking about the change in length, right? So elasticity in length, so we're talking about which one? We're talking about Young's modulus, right? So we write our formula like this. So it's going to be force over area, then Young's modulus, then the change in the length over the initial length. Okay, so then what are you trying to find? You're trying to find the change in the length. Okay, so you're trying to find the change in the length. So what do you do to make that the subject of the formula? Going to be okay. So that's that, right? So then what then you do now? So that's the change in length is equals to the force times the initial length over Young's modulus times area, cross sectional area, isn't it? So once you do this, really, the rest is just really just plugging in the values, I guess. So it's that. Then the initial length, they told us that this was a 4 meter thing. Young's modulus, again, we're using Young's modulus for what? Young's modulus for steel. Young's modulus for steel. So Young's modulus for what? Young's modulus for steel. So you've done that. Then you now put in now the we now want to put in the cross sectional area. Okay, the cross sectional area, the cross sectional area. So yeah, you just plugged in those values and you plug on the calculator. Ensure that you are not you do if you want you can do it separately, the top part, the bottom part, just to avoid what calculator errors. Huh? But because of the way maybe you may have entered the values. So yeah, so this was the change or the change in the length. Okay, so if they ask you to say what then was the yeah, so if they ask you to say what then was the length, of course you would easily calculate that. You know it's final minus initial, isn't it? But otherwise, the change in length, that was the change in length of this particular beam. Then now the second question is, what maximum load in newtons could the steel beam support before failing? So in this particular case, what you are looking at is what is the amount of the force or the pressure which steel can what steel can be exposed to without breaking, without failing. So that's why we now check the ultimate strength for what? For steel. And then you remember I said you have to check whether it's a tensile strength or a compressive strength. Tensile strength is more about pulling, huh? Then compression is about pushing downwards, huh? Or compressing, as we would say. So now what you're going to say, you're now trying to find the maximum load. So the maximum load you're going to say the stress we know is force over area, and then you know that the maximum, then here now you're going to put the what is equal to the ultimate strength. Why are you putting the ultimate strength? Because from this you know that the ultimate strength of course is in pressure, right? Or pascals, because even force over area is pascals. So you're just trying to say if once you equate this, it means that once your force goes above what we are going to calculate, it means that the ultimate strength for steel has what has been surpassed. And one thing that you would see is that the the greater the area, okay, so the greater the area, it means that even if a force is large, but the steel is going to be maintained. And this makes sense because you can imagine if you are building, let's say, an upstairs house, right? I'm sure you've seen the difference in uh the cross-sectional areas of the steel bars that they use when you are building a multi-story building, and when you are just building just a single floor house, right? I'm sure you've seen the difference in the cross-sectional areas of the steel bars that they use. Huh? So what you're basically, so here we are saying, okay, so the ultimate strength of what? So the ultimate strength of steel under compression, because this question is talking about compression, is what? It's yeah, so it's 5.0 times 10 to power 8 pascals, right? So meaning here now we know what the pressure, the what, yeah. So what that is, what the stress is, isn't it? So then we now want to calculate the what? We now want to calculate now the force, isn't it? We now want to calculate the force. So we know what our area was. Remember, it told us that the area was that. So then we are going to say force is equals to what? So if we want, we could do that. So force is equals to that, and then we are going to have that. Okay. So and then we have okay. So the ultimate strength of steel, which is that. So here, if you want, you may want to use the units uh, for pressure in this way so that they can cancel out. Huh? But of course, it's all about preference. So you do that. So you do that, and then you are going to have 8. Okay, so then you are going to have that and that, and then you would have let's look at our value. So you are going to have that. Okay, sorry about that. So you are going to have So you're going to have that. So that's 6 there, right? So 4 times 10 power 6 newtons. So it means that once this force is surpassed, okay? Once the force goes above this for this steel bar, it's going to what? It's going to break. Okay? So these are some of the signs. That's why you see like the elevators, they will say only this number of people are supposed to go in the elevator, or sometimes they even give a what? A force, okay? A weight, a maximum weight. Because you may be aware that elevators have got cables, right? So those cables may be strained, and the elevator, those cables can just cut, break, and then the elevator just falls down like that, right? So it's very important to be heeding rather to those instructions. So yeah, so that's pretty much about it. So now let's now look at this question. So this question, I really like it because it really brings about something that we did, which is the momentum. Okay, so that's the thing with physics, right? When we're doing deformation, ensure that you have got all your tools with you, because you never know just which tool will be required of you to be able to use, right? So don't say no, this topic is deformation of solids, so I'll just focus on this. No, always ensure, that's where practice comes in. Always ensure that all these things are at your fingertips, and once that's the case, you will not have difficulties. So we are saying a defensive lineman of mass 125 kg makes a flying tackle at an initial velocity of 4 meters per second on a stationary quarterback of mass. So of course, they are talking about American football, isn't it? So the quarterback is there, then the defensive lineman tries to ensure that he defends. So he goes with a flying tackle, moving at an initial velocity of what? Of 4 meters per second, and then hit on the stationary quarterback of mass 85 meters, and the linesman's helmet makes solid contact with the quarterback's femur. So okay, you've not yet done your anatomy, but femur is the thigh bone. Okay, so the bone that makes up the thigh, so that's what you call the femur. Okay, yeah. So they are saying that the helmet of the linesman makes contact with the quarterback's femur. So now the questions start. What is the speed or the final speed of the two athletes immediately after contact? Assume a linear, perfectly inelastic collision. So there now, that's the key thing. So they've told you there what kind of collision that was. So it's now up to you to remember to what's a perfectly inelastic collision. I remember the time when we were doing momentum, there is someone that asked to say, okay, but how can you determine and everything? So I said sometimes they will tell you, sometimes they'll just tell you the two athletes moved together, they fell together to the ground after the contact. So it's still the same thing, right? So what do we know? So we know that the momentum is going to be what? It's going to be conserved. So initial momentum, final momentum. So uh, between the two people who was moving in the initial phase, remember the quarterback was stationary. It was the defensive lineman. So for the defensive lineman, we are going to designate his mass with a capital M. Like they said in the like they put it in the question. So this is for the lineman, we use a capital M. Then for the quarterback, we use a lowercase m, letter M. So now, initial momentum. Who had momentum in the initial phase? It was the lineman, isn't it? So the lineman has initial momentum. The quarterback was stationary, okay? He wasn't moving, so he had zero momentum. But the final momentum, they've told us it's a perfectly what? Inelastic collision. So meaning they stick together. and then there you have a final velocity. Okay, and there you have a what? You have a final velocity. So here, so you see, here is just plugging in values. Okay, so we are taking the quarterback's direction. Oh, sorry, we are taking the lineman's direction to be the positive direction. Okay, so direction is always important. So we are going to have the defensive lineman has got a mass of what? Of 125 kg. Of course, he was moving at what speed? At what velocity? 4 meters. We've already said it's positive, right? Because we're taking his direction to be positive. Then what do? We add the masses. So the lineman was 125 kg. Then the quarterback, they've told us that he was 85 kg, isn't it? 85 kg. Uh, okay, then the final velocity. So then what you do is uh, okay, so you divide this. Let me, yeah, so that's pretty much about it. So there, that if you wanted, you can make final velocity the subject of the formula just to make your work neater, but either way, you get your value. Okay, but it's good to make it the subject of the formula. It's easier to plug in values like that. So, so that's about it, right? So that's how you go about it. So always ensure that you've got all your physics tools, kinematics, you've got the, what can I say? You've got those work energy and power. Always have them on your fingertips because you never know what you will be required to use. So if the collision lasts for zero point 0.1 seconds, estimate the average force exerted on the quarterback's femur. So remember, here they are now trying to test. Can you remember the relationship between force and what? Force and between average force and momentum. Remember, we said average force is change in momentum over a change in time. Okay, of which, if you want, you could then say you can cross multiply and say average force times time is the change in what? Change in momentum. Okay, so change in momentum. Remember, we are talking about the quarterback's uh, femur. Okay, okay, so we are talking about the average force exerted on the quarterback's femur. Okay, so how are we going to find that? We are going to find the momentum of the what? The change in momentum, the force that was with the change of momentum of the what? Of the defensive lineman. Because remember, it's the changes in the lineman that determine the pressure or that determine the effect that happens on what? On the quarterback, isn't it? Because it was him that was in motion and it was one that was hitting the other. So we can't use you can't calculate the force of someone who was hit and you're calculating that person's internal force. No, you always go for the external force, isn't it? Since it's what really hit the person. So change in momentum is mass times that, mass times final velocity, and then minus mass times initial velocity. So that's an important point to take note of. So what do we do? So we can factorize just to make it easier. So now we can plug in our values. Okay, so now remember that all this we're just deriving average force over what we've been able to find. So over change in time, change in time. So what we are then having is average force, then you're having that over change in time. So the mass 125 kg, and then the final velocity. Okay, so the final velocity. Okay, so the initial, so that was the initial there. Okay, so there is that. Okay, so then over the time. Okay, they've told us is 0.1 seconds. So so that's that. I know you might say, okay, that needs to have a negative. You can look at it like that, but yeah, but we're talking about the force that was being applied. So remember, we are looking at it from the context of what? The context of the force being applied on the patient's what? On the patient. Sorry, on the person's femur. So you could look at it like that. So yeah, that's why for the book, I don't know whether it was an error or not, but yeah, that's about it, right? So, oh, sorry, I made a mistake. It should be 2.38. Yeah, that's what we solved for. Yeah, so really, that's basically the thing about it. So that's basically the thing about it. So yeah, that's about it. So then, now the third question: if the cross-sectional area of the quarterback's femur is equal to, so now we've now started now we've now gone now to our topic now. Now they are saying if the area of the quarterback's femur is, so they're saying the area, so that's the femur, that's the cross-sectional area of the quarterback's femur. So calculate the shear stress exerted on the bone in the collision. So again, remember, that's why I kept on stressing on last time we met to say that's why you have to know what is stress, what is strain. Because if you don't know that definition, then you get stuck, right? So we know that the stress, so the stress is the force over area. But in this case, they've told us the shear stress. But it's the same thing. It's over here they're just being specific to what deformation we're having. So what's the force? It's what we found. So really, for these questions, once you get a hold of them, whenever you see them, you can always be sure that you're going to get full marks because it's just about the analysis. You just analyze the question and then uh, everything falls into shape. Everything falls into shape. Okay. So Pascals, right? So that's basically how you would go about that those kind of questions. So then, before we can talk about how pressure varies with depth, so we'll talk about I will look at another question. which will talk about the bulk modulus. Huh? So we should talk about the bulk modulus. So, okay. So, so ships and sailing vessels often carry uh, often carry lead ballast in various forms, such as bricks, to keep the ship properly oriented and upright in the water. Suppose a ship takes on cargo and the crew jettisons a total of 0.5 meter cubed of lead ballast into water 2 kilometers deep. Okay, calculate the change in the pressure at that depth. B, the change in volume of the lead upon reaching the bottom. Take the density of seawater to be 1.025 times 10 to power 3 kilogram per meter cube, and take the bulk modulus of lead to be 4.2 times 10 to power 10 pascals. So here the key thing is not to panic, just to go through this question step by step. Okay, so it's just to go about this question really step by step. So one thing first that you want to calculate is so from this question you may see that we are looking at the pressure difference between the surface of this sea and also there was this and a depth of 2 kilometers, and so this is going to be, so the pressure difference is going to be due to the weight of the what, due to the weight of the water column. Okay, so uh, this particular thing has gone deep into the water. So what then becomes important in this is for you to calculate the what, to calculate the weight that this water column had. Okay, so here is the thing. Uh, Remember that question that we started with, right? Where you dip something in water and then we were able to calculate the weight of this block. I remember that question, right? We were able to calculate the weight of this block, and in calculating the weight of this block, it was actually giving us more or less the the forces which were actually giving rise to the what? Which were actually giving rise to the pressure. And so once we find the weight of this particular of this water column, okay, then would have now figured out what? Would have now remember pressure is what? Is force over area, right? So meaning that then we would have now figured out the so would have now been able to figure out the what's this the pressure of this particular thing. So that's something that's very, very important to take note of. So having done that, I don't know if there are any questions. So that since we've really done a number of things, so I want to ask: are there any questions with regards to this? Okay, so if there are no questions, so then what we are going to do is okay. So there we have it. So the key thing, we're going to calculate the what? We are going to calculate the weight of the water column. So how do you calculate the weight of the water column? So we know that weight is going to be what? Weight is mass times gravity. Now remember, we know something about density, right? So they've given us density. Density is equals to mass over volume, isn't it? So uh so we can substitute and say mass is equals to density times what? Times density. So we have been given the density and we've been given the what? Yeah, so we've been given the density and we've been given, we know what G is, and what else? And of course, the volume we've been given. So you may be wondering, it's okay, but where is our volume coming from? So this is the thing, right? So they've told us that this thing went down by what? 2 kilometers. So, in as much as that mean, okay, so you can actually use the density, the volume, and acceleration of gravity to calculate the weight of water in a column having cross-sectional area of what? Having that. So that particular depth that we are talking about, we can actually be able to look at it as what? As our volume. Because remember, this is what this particular water column is what? Is going to be covering here, right? So that's what we have there. So meaning that our density they've given us, so our density is going to be, okay, so let's just write this. So weight is going to be, we substitute density. So density usually they write it like some form of a p, but just to avoid mistaking it for momentum, I'll just write a d, but the official one anyway, let's just write the official one, but just know that it's density. Okay, density, then v, volume, and then the gravity there, right? So then what you then are going to have is density is going to be, so there, right? Then uh so where are we, you know, volume is equals to what? Mass over density, okay? It's equals to mass over density. So okay, so now we're now getting our volume. I can't explain earlier on. So we've gotten that, right? So now we now get our G. So our G, then together, all together, we're going to have a value of 2.01 times 10 to power 7. Let me write that properly. To power 7 newtons. So there you have it. Then, so that was our, so we are still solving for A, right? So there we now just found the what? The weight of this water column. So after now finding the weight of this water column, then what then we are going to do is, remember our main question is what? Is to find the, okay, so remember our key aim here is to what? Is to find the pressure difference that was occurring here, right? So what we then do is we now have to divide by what? We divide by the area. Okay, we have to divide by the what? We have to divide by the area. Okay, so remember that the water column is the cross section area of what? Of 1 meter squared. Okay, so that's something that we have to take note of. Okay, then the volume, I already talked about how we found that. So then we can now go to the change in the pressure. So the change in the pressure is going to be force over area. So force over area. So the force is what we found. And then remember the cross sectional area of the column of water is what? 1 meter squared. So basically giving us the same thing, right? Okay. So this was something that we reviewed when we had just started this topic. So I'm sure. Yes. Okay. So uh okay. So like for this particular okay. Would what I would say is that it's more or less like more of a standardized thing. But of course, if the question says otherwise, yeah, then that should be the case. But yeah, whenever it comes to a column of water, a wet column of water, I think yeah, that should be it. But of course, the more you solve, maybe perhaps you may be able to see that. But usually, when we talk about the column of water, it's that's really the thing. And then also one thing that we have to take note of is sometimes certain questions may be silent on certain things like this. But anyway, let's see what the question is telling us. Cause okay, so suppose a ship takes on a cargo, and the crew jettisons a total of 0 point. So that's they're talking about the volume there. Okay, yeah. So it's something that you would want to take with caution. So there may be certain times where, but what I would think is that it's usually something constant, unless they state to say, okay, we are looking at a cross section area that is different. Yeah, but when it's just silent the way it was, you just calculate the weight of water in a column with cross section of what? Of 1 meter squared. So, but again, uh, different literature will say different things. So I don't really say this is this, this is that. But usually, when the question is silent about it, you would want to take that approach. So you'd want to take that approach. Yeah. So then now we can now go on to calculate our actual question related to this. What really the question is. So let me just be able to let me just plug in the charger so that this thing doesn't go off on us. Okay, so that's really about it. So yeah, so what I would say about that is that it depends. It depends, but usually I'm not saying always, but usually it's going to be that. Okay, so having said that, yeah, so that's pretty much about it. So it goes with the more you practice questions. I'm sure you have got that Shom's book that I uploaded on Google Drive. So trying out questions is very important with what with physics. Okay, so let me just try to set up this. Just give me a moment. Okay. Okay. Yeah. So sorry about that. Yeah. So that's basically about that. So usually when the question is silent, you want to go down that route, but of course, trying out a number of questions would be helpful. But usually, we take it as so calculate the weight of water in a column with cross section to be that. Okay. So now, the second part of the question then asks us to uh, find the change in volume of the lead upon reaching the bottom. So here they are talking about the change in the lead. So whenever you hear change in the lead, then you know you're talking about what? You are talking about bulk modulus, isn't it? So change in pressure is equals to minus B. So we discussed and explained why that minus is there. And then yeah, so once you have that, then you change the subject of the formula to be that, and then you're going to have negative V change in pressure over uh, B there, isn't it? Okay, so we found that there. So uh, we know that the initial volume they gave us to 0.5 meter cube for the lead. Then the change in pressure is what we've calculated using the weight of the column of water. Okay, so the column of water, then okay, then power 10 pascals. Okay, from what we calculated, then all over the bulk modulus which they gave us, the bulk modulus of lead, which was 4.2 times 10 to power 10 pascals. Okay, so what then are we having? So we are having minus 2.4. So the pascals are cancelling. So minus 2.4 times 10 to minus 4 times 10 to power minus 4 meter cubed. Okay, so what this tells us, so this means that if the change is a negative, then this means that there was a what? There was a compression, or there was a reduction in the volume of this, which is what we would expect, because going downwards, going underwater, you would find that the pressure increases, because remember, pressure increases with depth, isn't it? So expect the pressure to be high, and because the pressure is high, there's going to be pressure on all sides of the of this steel. And so what's going to happen is there will be that change, that decrease in the volume of that steel. So that's an important point to take note of. Okay, so then we now talk about okay, so here they're just trying to explain arches and ultimate strength of materials. So here they're just trying to say usually how you set up something can really affect the ultimate strength. So with certain ways of building, you'd find that the same material, but when it's just been put and arranged differently, you would find that it may appear and it may show greater strength simply by just how it's been built. So this is just more of like application. So it's just application of what we've discussed. But yeah, okay. So now where the money really is something that I'm just from talking about, where I said pressure uh, changes, or there's pressure changes with depth, and this change is an increase in pressure, right? So what happens here is that when you've got when a fluid is at rest, let's say when you've got let's say water in a container, uh, all portions of the fluid are going to be what? Are going to be in static equilibrium, because they are not moving and nothing else is happening, right? And so what this means is that uh, when if you were to draw something on there, okay, let's do this. So if you have something like this, all points at the same depth must be at the same pressure. So meaning that if you've got this point that point. So there is this point, that point on top, and then there is then this point, and then there's the last point, right? So those are what? Those are levels, right? So those are levels that I've set up. So there's first level 1 or level A, B, and C. So what this basically tells that because these are at a particular level, it means that the pressure in the level A, all the particles have got the same, have got what? Have got the same pressure. Okay? And then level B again, because they are the same depth, the same thing, up to D. Okay, so I'm sure you may remember doing a particular experiment where we would be where what we used to do was you would get so what was happening is I think you'd have something like this, and then they used to open something like that, right? Like they would make maybe about three openings, then there would be water here. And what was observed was that the lowest one would have what? The highest pressure, followed by this one, and this one having the what? The least pressure. And that's why you'd see that those water tanks, there was this those pipes are put where? At the bottom of the what? Are put just near the bottom of the tank. Of course, the idea is for what? The idea is because as the depth increases, the pressure increases, right? So there is just the derivation, but not really an issue. But what's very important is just to understand this particular equation there before we can solve that example. So what that basically says is that so according to equation 9.11, so what we are basically looking at is the pressure at a depth h below the surface of the liquid open to the atmosphere is greater than atmospheric pressure by the amount pgh. So what this basically is saying is if you've got let's say you've got a container, right? So you've got a container. So if you've got a container, then you've got fluid, you've got fluid. Okay, so let's just put like that, right? So if you've got a container and you've got fluid, what's happening at this particular point is here, remember from that question that we did last time, at the surface, you've got a what? An atmospheric pressure. So this is what we are putting as PO. So now there's an atmospheric pressure. So meaning all the molecules, all the water molecules here, they're having what? This particular pressure. So meaning if you're calculating the pressure of this particular point, you're just going to say, oh, it's just atmospheric pressure, isn't it? But then what happens is that as you go down, there is now an increase in the what? In the atmospheric pressure. Now, this is going to be defined by what? It's going to be defined by the density of the substance. So remember, density we say is represented by P, okay? By that okay, that P, then G and H. So what does this mean? What this basically means is you are looking at what? The density of this fluid. And it makes sense because you may see that the the more dense a fluid is, you would expect that the more pressure it's going to be putting on the what? On the surface of this container, isn't it? Okay? Yeah, the more dense. I'm sure you may have tried carrying something heavy in a plastic and the plastic just rips open. Why? Because the density of that substance that you've used to carry that, so the pressure has increased downwards, right? And then the plastic gets damaged where? Down, not on top. So that's the key thing. So the density there is important. Then where does the gravity comes in? The gravity comes in because it's the weight of this particular substance that we are talking about. Okay, so it's the weight of this particular substance that we are talking about. And whenever we are talking about weight and depth, remember we can't do it without what? Without gravity. Because gravity then it's the one that tells us, okay, you've gone up, you've gone down. So therefore, that's where the G comes from. Then the height, of course, where there is gravity, then you always have to take into account the what? The height, because it's the height that's now going to give us the range there, and you know how the by how much the impact of gravity is going to be. Because if, let's say, if, because the surface is what? The surface is h is equals to what? 0 meters. The surface, because remember we are going downwards, right? So if you say that the surface is 0 meters, meaning all these components that I'm now putting in a square is going to be zero. So mean that it's going to be, your total pressure is going to be what? It's going to be atmospheric pressure. So therefore P is going to be what? P. Oh, okay, atmospheric pressure. So that's why that's going to happen. But as we go below, let's say maybe here, maybe let's say we say it's now maybe let's say 0.5 meters, right? Then now we can be able to plug in, because we know the days, let's say it's water, then gravity, we know it's 9.8 meters per second square, and we can plug in that height. Then we are now going to get the value of the what? Of the PGH. Now we know of the density times gravity times height. So then we are now going to know what that increase was, or that change, that increase was in pressure. And so when we add to the atmospheric pressure that is already occurring at the surface of the fluid, then we are going to know the pressure at this point, where the depth is 0.5 meters from the surface. So basically, that's really yeah. So that's why I didn't really dwell much on how they were deriving, because just that particular equation is able to explain quite a number of things. So when we meet on Wednesday, uh, this is where we'll be able to start from, or rather, that's where we'll be able to continue from.